So hello everyone, my name is Jacopo Poli and I'm the lead of machine learning at LightOn. We are a startup based in Paris and we build innovative light-based hardware for machine learning at scale. And today is the 10th edition of our LightOn AI Meetups. And for this edition, we have Krzysztof Choromanski with us. He's a research scientist at Google Robotics in New York, and also an adjunct assistant professor at Columbia University. And today he will be talking about rethinking attention with performance and about this new revolution that's coming. So yeah, I just leave leave Krzysztof to his presentation. I'm gonna stop my screen sharing and you can share yours, Krzysztof. Thank you.
Thank you so much for the introduction. Let me quickly share my screen and to start. Okay, perfect. So it's a great pleasure to give this talk. My name is Krzysztof Choromanski. I'm a research scientist at Google Brain Robotics team in New York. And well, this talk will be about a recent work of mine with my collaborators on efficient transformers architectures. Actually, recently accepted to ICLR for the oral presentation. And as you see from that graphics, it will be really all about doing attention more efficiently. We'll be disentangling something, and I will explain what exactly we are disentangling during the course of the talk. So yeah, so the class of architectures that we propose is called performers, because as I said, we want to really focus on improving space and time complexity of transformers architectures. And I want to emphasize that it's a joint work of lots of researchers from Google Robotics, Google Brain in general, Google Research, University of Cambridge. We have collaboration with the team working on bioinformatics applications in Google. So it's a really joint work of lots of people. And we have the code publicly available. We actually are excited to see that people use performers in the applications. So they are applied also externally outside Google, which was our goal. And yeah, let's start. So before we go to transformers and performers, why attention is important in machine learning these days. So it's really all about memorization. So people just realize that purely reactive policies, if we talk about reinforcement learning and robotics, it's maybe not enough to solve challenging tasks. So I'm in the robotics team, and my angle is somehow biased towards robotics, but this attention-based architectures obviously are used presently, mostly nowadays, in natural language processing. So the idea is that you would like to memorize your data and tokens from the past, and make sure that you can leverage this information to make decisions. This decision can be an action that is proposed by a controller, can be a result of the classifier. So here what we see is, you see the videos of the agent traveling in the maze. And here, of course, well, we can imagine that memorization is important. You would like to figure out which parts of the maze you have been to, so that you can efficiently explore and accomplish a task. And the other task here is, I think it's a scripted policy for solving Hanoi towers. So the point is that long horizons, where you need to memorize and learn complicated dependencies between different tokens, potentially long-range dependencies, this is what becomes more and more important in machine learning. And obviously it all started, I would say this hype started with the paper, Attention is All You Need. And we have proposed transformer. Transformer is an example of the attention-based architectures that is trying to learn these complicated long-range dependencies, but it's a really modular architecture that it has attention modules and standard fit for fully connected modules. Needless to say, the critical part that makes transformers state-of-the-art in natural language processing is attention. So we'll look more closely into attention. The problem with standard memory-based architectures is, well, space and time complexity. If you have very long sequences, creating attention tensor is just not feasible. And that's something that we would like really to address in this paper and in the performance project. So let's talk a little bit about like extra motivation, right? Like, so here you actually have an example of the hybrid attention, right? Like, so when we talk about attention, usually we think about memorization. So you have an agent here with the vision input. You see the video, a bunch of frames. You can attend over time, but you can also attend over space, right? Like, so an agent might try to figure out which parts of the image are more critical for making particular decisions. For instance, to navigate in the complicated environment, like navigate car driving like in the city. So in that setting, we have actually a hybrid attention where you have both temporal and spatial dimensions. And the way attention works is that, well, I show it on the example of spatial dimension here, is that, well, it works on the bunch of tokens. Those tokens in the context of the spatial dimension will be patches of the image. If we are talking about temporal dimensions, that will be like whole frames. And you linearly project those features. You really think about those as features, and then you compute the attention matrix, like which you can think about as the kernel matrix, a matrix of similarities between different tokens. So you define some similarity measure. The problem with the standard approach to attention is that it's not very scalable, because in order to compute that dot product matrix, so the softmax attention matrix, you need the time and space, which is quadratic in the length of the input sequence, right? Like if you have spatial attention, this length will be the number of patches, like even the number of pixels. If you have temporal one, it might be like the number of frames in this example. But so for long range attention, this is questionable. And of course, like in the robotics applications, when you want to deploy those architectures on real hardware, that's even more tricky, because you have restrained computational resources. And so even inference is problematic, even if you can train with the standard brute force approach. So what we don't do in the performance paper, where we propose this new attention mechanism, is sparsification. So first I will say what we don't do, because this is what people usually do when they try to make attention more tractable, and then I explain what we actually do. So the standard approach like will be just localize attention. Let's just, so by the way, this rows here correspond to different tokens, and columns also to different tokens. And the entry of the attention matrix, think about it as a similarity score, how relevant two tokens are, how well they attend to each other. So in the standard sparsification approach, you just say, well, the tokens attend just to other tokens in the neighborhood. If you think about graph attention approach, this sparsification prior is actually given by the graph structure. So the standard graph attention network proceeds by where the tokens attend just to the immediate neighbors. So that of course sparsifies the attention, and that helps in terms of space and time complexity. But this prior might substantially harm accuracy. So what we want to do is we do not want really to incorporate any structural priors of the attention matrix, because actually in most practical applications, it's a dense matrix. So can we somehow improve the computation of the attention module without really adding this strong priors that sometimes do not really make sense? So the idea is to use kernels, or well, in particular random feature maps, but the randomness is just one particular feature of our approach. We can also use deterministic features. So the very rough idea is, let's take this attention matrix that encodes the relationship between different tokens, and let's try to decompose it, somehow disentangle like this stuff like into two simpler matrices, Q prime and K prime transpose. So you have, at least on expectation. So we can think about the tensors on the right-hand side as potentially random tensors. And it turns out that we can actually do it. There's a very easy way to do it for the standard attention matrix. So in the standard attention matrix used in transformers, the similarity between tokens is defined by the so-called softmax kernel. So that's the formula. And it turns out that you can decompose this attention matrix using, well, the standard theory of random features. We actually were surprised that we realized that nobody actually proposed this like before. It's really lowering the composition of the attention matrix into simpler matrices that gives you unbiased estimation. So you can actually use random features to produce unbiased estimation. Well, the story is a little bit more complicated. I will explain in a moment why this approach actually doesn't work. It almost works, but there are like some extra ideas that need to be implemented. But that's pretty much the setting. You try to represent your kernels, your similarities as dot product of kernel features, and then you decompose your attention matrix into simpler ones. Now, why this is useful? Well, because of that figure, right? Like if you can decompose your attention matrix into simpler ones, then you can change the order of computations when you compute the attention module. You don't need to necessarily explicitly materialize the attention matrix. You use the decomposition and matrix associativity property, and by not explicitly materializing the attention matrix, changing the order of computations, you can actually avoid quadratic time in the number of in the length of the sequence. Of course, now your complexity depends on the number of kernel features that you have. So the question is it possible to use like relatively short, small number of these features? And the answer is yes. I will talk about it in a moment. But the point is that this trick can be actually used also in the causal attention. Like in transformers architectures, we usually have two settings: the bidirectional setting, where every token attends to every other token, and the unidirectional, or the causal setting, when there is an arrow of time and the tokens attend just to the previous tokens. Think about, for instance, an NLP setting, where you would like to use transformers to create phrases of text, right? Like it's reasonable assumptions to assume that the context of the word in the given sentence depends on the past, doesn't depend on the words later. So those priors can be incorporated also into performance architectures. And the rough idea is that you can represent the so-called masked attention, because I mean, it's a masked attention by the so-called prefix sum computations. I won't go like too much like into details here, but the point is that you can use low-rank decomposition also in the causal setting. So why this is not the end of the story, right? Like it seems that, okay, so we have this low-rank decomposition. It's we can do it even in an unbiased way. Well, end of the story, right? But so it's a little bit more complicated, and that's what is actually really exciting. So what's going on? I'm just checking that I have like about 15 more minutes. Is that this approach actually won't work out of the shelf. So the problem is that it's not really a good quality approximation. So you can use relatively small number of random features to approximate, well, every individual entry of your attention. But in transformers, at least, what we do when we apply attention is we also renormalize attention. So we want to make sure that the scores in every row sum up to 1. And that's that is a problem, because then we ultimately need to compute the renormalizer. And you have lots of entries in the renormalizer. Each of these entries you approximate with reasonable performance, reasonable accuracy, but the approximation of the entire sum might be arbitrarily off. And actually, if you use the standard features that I just showed you for the softmax kernel, the sine, cosine, trigonometric features, then you are super inaccurate when the entries of your attention matrix are very small. And unfortunately, most of the entries of the attention matrix are actually small. So even though in principle it should work, actually it does not. This plot here is a ratio of the mean squared error of the trigonometric variant, the standard variant that I just showed you, and the new one that we are proposing, the so-called favor plus variant, a new way of constructing features for the softmax kernel. So what you see is that those tower functions here, those towers here really correspond to the regions where you have very small value of your attention. And one of those estimators, the standard one, is just arbitrarily inaccurate. So it just doesn't work. Whereas ours is, the variance of ours actually goes to 0 as the values of the attention matrix go to 0. So it becomes arbitrarily accurate. And And this is pretty much represented. This is the slice of that plot, the 2D slice of that plot. So those asymptotics really correspond to those regions where you have very small entries. And it really illustrates the fact that the standard way of approximating, it breaks down. It doesn't work. You are super inaccurate. So the so-called favor plus mechanism, which construct features that are always positive, resolves this problem. And let me get to like some results that we have like with this scheme. So what you see on the left-hand side is the comparison of the standard transformer with the performer. So the x-axis is the logarithm of the length of the input sequence, and the y-axis is the logarithm of the forward or backward pass. So what we see is that by doing this decomposition, favor plus the composition from performers, we can actually proceed with much longer sequences. Those curves end when we are running out of memory. So we can work with sentences of length 2 to 22 with performers, whereas for regular transformer, dashed lines 2 to 14 was the max here. And this black curve right here with this process, this represents the so-called dummy transformer. So in the dummy transformer, the attention is not really doing anything. So you can think about it as the upper bound of like whatever you do with the attention, like it cannot be better than this black curve. And we are pretty much very close to it, which shows that there is not that much more room on the top of favor plus mechanism that you can leverage to further improve the attention module. And on the right-hand side, we see I mean, there are two interesting things. One is that we use like certain like mechanisms for constructing these random features. Well, Monte Carlo mechanism, the so-called orthogonal random feature mechanism, which gives like substantial accuracy gains over the standard one. So what I want to say, there are lots of like extra tricks that are actually incorporated to make it work. And the backward compatibility, what we mean here is that you can actually train your transformer with the regular mechanism and then use this new mechanism to uptrain it or even for inference. So that is very nice feature because you don't necessarily need to train from scratch with this mechanism. Also, like I want to mention that you don't necessarily need to use those random features for the softmax kernel. You can use actually even deterministic features. You can choose any kernel you want, to be honest, and apply a performer's technique to decompose the attention matrix and improve space and time complexity. The reason why softmax is particularly important is that it gives really good quality models. It's really hard like to get like with much better kernels than the softmax kernel. But the mechanism is not restricted just to this. So some results that we got, this is standard text data, where we see that, well, in this case, transformers can actually be applied right away because the sequence is not that long, 1024 tokens. So we can explicitly materialize attention and compute regular transformers. And what we see is that we can actually match, right, like exactly like the, I mean, effectively the accuracy of transformers with performers. Whereas with the new mechanism, right, like you see that the sine cosine standard mechanism that I guess like researchers try to apply it like probably there before just doesn't really work. But it really, if you have like a better one, that's a game changer. Here, and another example, I would say it's much more interesting because it's vision, right? Like vision is particularly useful because it's all about long sequences, ImageNet 64, and 12,000 length, right? So the regular transformer is not even feasible, but you can actually run performer. We compared like with other class of scalable transformer architectures. And what we pretty much conclude is that we can get very good accuracy with many fewer layers. So this is the gains that we have from the performer. And yeah, this is a performer ReLU. What it really means is that it uses a ReLU kernel. I just said that there are lots of different kernels that can be used in performers, not just the softmax one. This is the softmax kernel, this positive softmax. The conclusion is pretty much here, you know, both kernels work really well. So you don't necessarily need to use softmax. One of the most exciting applications, and I'm looking at, I have like about a few more minutes, is for protein design. Why this is particularly important? Because this is where long-range attention potentially might be critical. So usually the way transformers are applied for protein design is you think about the sentence as a protein and the words as amino acids. So the tertiary structure of the protein is what is really important and what implies a functionality of the protein. Well, there was like the famous, right, like result of AlphaFold version V2, which predicts the 3D structure of the protein from the 1D structure. So this is a really big thing. And the point is that if you keep the 3D structure, the amino acids, the words that are far away in the primary sequential structure can end up to be very close in the 3D structure. And actually those pairs determine the shape and effectively the functionality of the protein. So you have like a long-range attention here. Now, the question is like whether you can sparsify this attention or not, that's open. But you definitely don't want to use local attention. And what we really do here is we show that you can do protein modeling with performers. And first of all, you can reach regular transformers. The important thing is that when we go to complexes of proteins, those lengths are much larger. So then the regular transformer architecture is not feasible. So this really shows that you don't necessarily need this regular transformer architecture because you are matching accuracy or even outperforming. Interestingly, the performer ReLU variant here is actually improving. This is standard masked BERT task, improving like on the upon like the standard attention. And this is like the proof of concept on what I just mentioned like a minute ago. If you have much longer sequences, you can think about complexes of proteins, regular attention just doesn't work. It's not feasible. In order to run regular transformer, you need to decrease the number of layers, and that hurts the accuracy. You don't need to do it with performers. And interestingly, performers find actually in attention patterns that are somehow different from standard attention patterns found by transformers, even though you see that the accuracy is like pretty much matching, or even like, I mean, we get some like extra gains when we use other kernels. So we have a collaboration with the team that has expertise in bioinformatics, and they actually were pretty excited about this and seeing that performers are able to find the dependencies between amino acids that they know that they should be there from the biological knowledge they have. So it works like really nicely. They were also tested, I mean, performers in the so-called long-range arena. Actually, that paper was also accepted to ICLR recently. So here, performers are compared with a bunch of other recent transformers architectures, efficient ones as well as maybe not that efficient, right? Like, so the question is where we are. And by the way, the paper is not our paper. So this results were done completely independently. So we were very happy to see that performers are doing well. They are getting like really good accuracy, average accuracy, like on tasks. They are actually the fastest mechanism from all the compared mechanisms that you see here. And this plot basically shows where we are, right? Like, and again, this is a plot like from this paper that is doing comparison. So if you think about something that is really fast and accurate, performer is, I would say, the best choice. Standard transformers architecture as well, they have the memory footprint that is like too big, like for long sequences. So this long-range arena score is the score like from this task where we are particularly interested. Well, I mean, not us really, but because the experiments were done by other authors, they're particularly interested in a task requiring long sequences and comparing different methods. So that's it on my side. And I guess, yeah, I made it in 26 minutes, so I'm happy. And if you have any questions, I guess that's a good time right now to discuss. I'll be very happy to answer. Thank you so much.
Yeah, thank you, Krzysztof. It was a really nice presentation. Yeah, this is the time for questions. So if you have any, you can either unmute yourself and ask the question, or you can write them in the chat, and I will read them to Krzysztof for you. So anybody has any question? Otherwise, I will start with some of mine. Okay, there is one in the chat. Let's see. So Etienne is asking, would this also generalize to all normalization transformers?
Yeah, definitely, right? one thing, oh yeah, there's, oh, that's another question, right? Yeah, so the answer to the first question is yes. And the really nice thing about this class of methods is that they're extremely flexible, right? Because they can actually be combined like with a bunch of different architectures. Because what you really just modify is the way how you represent the attention matrix. So for instance, right, I mean, just to kind of like expand like on that question, we successfully incorporated performers into reformers, right? Like, so you can use favor attention from performers and reversible layers from reformers. In principle, actually, there is also nothing that would block people from using performers in sparse transformers, right? You can think about extremely long sequences where you conduct some sparsification, but within the cluster or a bucket like of the hashing mechanism, you still have long sequences, and then you apply favors performers in order to further improve space and time complexity. So it's a really it's a class of very flexible architectures, and that's why we incorporate them to many like standard transformers pipelines, because they are really targeting just the attention, improving like the way how the attention is computed. So that's the answer to the first question, and there was another one. Let me.
Yeah, this is my colleague Amélie. In what cases is sparse attention not a good idea?
Well, I mean, one case is where, well, I would let me clarify, right? Like the approach to, so first of all, if you have dense long-range dependencies, right? Like that seems like it's not necessarily like a good idea. And that might be in particular the case, well, in bioinformatics. So what I just showed, let me get back to one of the previous slides. Okay, right, like this plot, right? So on the left-hand side, you see standard BERT task with, we compare in particular performer with the reformer, which is a sparse transformer, right? That is using hashing in order to sparsify. And you see that what's going on with the accuracy. Now, the point is that I'm not claiming that that's necessarily the proof that you know, sparsification hurts there. It might be the case. There are other modules like of reformers that are different, in particular reversible layers, right? Like, so in principle, you know, some harm might be caused also by reversible layers, right? Like we don't really know. But the point is that we definitely have settings where state-of-the-art sparse transformers fail. We know it right now, and that's now it's also kind of like intuitive, like to see this, right? Because you know, most sparse transformers techniques rely. So I would say even this, right? Even if you can assume that this sparsity is a good prior, what we currently have on the market in terms of sparse transformers, I would say it's not enough, because usually the approach is do clustering, or you can do clustering, you can do hashing, right? Like, so you try to chop your sequence into, or your set of tokens into subsets. This can be learned. This usually is learned, right? Like, it's usually a good idea to do it. And then you say that, okay, there is no any attention between tokens in different buckets, right? Or different clusters. You just model attention within each bucket. And you try to learn those buckets. So the point is that if your attention is sparse, right, but it doesn't have like this structure, right? Like you may have a sparse graph, but the graph that cannot be partitioned like into smaller number of small number of components. Large number of smaller components. That's what I mean. Then you have a problem, right? Then whatever you will do, like with clustering or bucketing, you will just get rid of potentially important edges. So what I claim is that even if you assume that sparsity is all that you need, it's not really clear. We don't have like a good general way of doing sparsification right now. The methods, like usually, they pretty much like rely on some way of chopping like into subsets, like partitioning into subsets. And I claim that you may have a sparse attention that will be hurt by that. But in general, you know, there are applications, in particular in bioinformatics, where where that's really a problem. Like you have like a huge gap, like if you do sparsification. Again, because in those sparse architectures, like usually there are lots of other things going on, not just sparsification, but like other modules, then I'm not claiming that, you know, what you see like on that plot is a proof that you don't want to sparsify, but at least, you know, it's a good like evidence that it's worth like to explore the role of sparsification and the quality like of the results, right? So this is kind of like, I would say bioinformatics is the most exciting setting, but people also realized that in other contexts, even like in the standard like NLP context. The other important thing is that, well, we know that regular attention works really well, right? Like, so sparsification hurts in general. So the question is whether you can actually, so if you can train, right, like with good like resources, the dense stuff, can you actually like uptrain, right, like with something that does not do sparsification, because that model won't be compatible with the stuff that you use for pre-training, right? Like, so if you use sparse architectures, you need to be consistent from the very beginning, right? You need to train with sparse, you do inference with sparse. So you cannot just like use sparsification like out of the shelf on the top of the mechanism learned with softmax. That's not the case here, right? Like, so what we really claim is, I would say, if you don't need to do sparsification, why to do it, right? If you don't need to add any strong priors regarding the structure of the attention, why to do it? Why you need to do it if you get like a good space and speed without it? And the answer is you can do it without it. So there's no reason to have this like back of like this like inductive prior that doesn't like necessarily make sense in lots of applications. There are settings when it's very, very effective, right? But what I claim is that it's not necessary, right? Like it's not necessary, so why to add it?
Okay, thank you for the very clear answer. Other questions?
Sure.
All right, I can take one. So first of all, great work.
Thank you.
I was thinking about like training the model. Is it a difference in like difficulty? Do you need to add like a gazillion hacks to make it work, or does it just work out of the box like you want it to?
It works really out of the box. I would say that you know, performance is a class of architectures where you can use different kernels, right? So in particular, you can use also deterministic kernels, right? Like one of those kernels that I presented is a ReLU kernel. So pretty much you have deterministic projections and you apply ReLU nonlinearity. This is a particularly simple task because you don't really have like any extra hyperparameters, and it usually just like works out of the shelf. And so we applied it like other people applied it. That's why exactly, you know, this long range arena paper, like we had no idea about those autos like running our performance. They just took something and like with some like default like setup and just works, and that actually works like pretty well. So I would say that you know, it's much easier to work with that and train with that like with that other architectures when we need to be like much more cautious. Now, if we talk about variants of performance that use random features, well, this is important because they can approximate accurately softmax, which is usually better than other kernels. Then you know, what you need to be aware of like is kind of like how many random features you really want to use, right? This is like a hyperparameter that probably the only one that is kind of like you need to be like more cautious about. More random features means better accuracy, but also less computational gains. So fortunately, the good news is that, and that's what we observed in a bunch of experiments, is that usually about 200, 300 random features is enough. So it's not really much difference if you go like from 300 features to 2000 features. And in order to get space and time complexity gains, if you use the randomized setup, if you don't like the deterministic one, then you know, as long as the number of random features that you use is substantially smaller than the length, then you have wins, right? Like so really for longer sequences, when you have thousands of tokens or tens of thousands, this is a particularly attractive choice because with about 200, 300 features, I would say that it will just you know, there is no really big like amount of tuning that you need to make, right? Like in order to like figure out like whether you can get good gains, you should just like use like out of the shelf like 200, 300 random features, and you will have the answer. So I would say training is pretty straightforward. And of course, the nice thing is that, it's really just the attention module, right? Like you can use your favorite transformer architecture, just plug in this attention module, right? Like, and that's really what performers are. They are not like really end-to-end like transformers architectures, a way like of improving attention that we apply it in transformers. But you can even like imagine settings where, beyond transformers where to use it. So it's a relatively straightforward training without like any kind of like sophisticated like hyperparameter tuning. That's kind of like the answer. That's why like we like it, because we ourselves like want something that will be easy, relatively easy for the task that we work on internally in our project. So we won't need like to kind of like spend hours like to figure out what is the right number of random features, what's the right kernel to use, etc. Yeah, but yeah, very good question. Thank you.
That's great. Thanks.
Great. There is a new question in the chat from Jean-Baptiste. Is redraw a trick needed to train performer to match transformer?
Right. So this is a really good question. This is a really good one, and I would say that we have mixed results, like with the redraw. So in principle, you want to redraw, and I guess that's the default setting in the open source version. Because at every step you are doing some Monte Carlo approximation of your attention tensor. This is really what's going on. So the idea is that if you don't redraw, if you are unlucky and you get like bad projections, then well, you are stuck with these bad projections like forever, right? And that will be problematic. And we observed settings where that's the case, right? Then you just like need to redraw and the problem is solved. So I would say that redraw is a good default. But interestingly, there are settings where we observe that without redrawing, you can actually even like improve on the top of like redrawing. So I would say this: the short answer is redraw is a good idea, right? That's why it's a default, and that's what I would start with. But there are like applications where by no redrawing you can actually like do like even better. There are like those like where no redrawing like hurts, right? Like so. If you want like kind of like a quick experiment, I would probably start like with redrawing. But in our settings, right, we tested like in the NLP context, we observe is that very often actually by just freezing at the beginning those Gaussian projections and just using them from now on, we can actually like even improve, and we have like much better accuracy. So so this is like a little like it's interesting like really to see what's going on there. There's not that much clarity like in terms of like theoretical. I mean, we don't have like good like theoretical insight. The intuition is that you would like to redraw, but the other thing is that when you redraw, you also want to make sure that you synchronize your seeds, right? Like so that there are kind of like redraw like requires like a little bit more care. I would say that, I mean, as I said, like 5 minutes ago, right? Like it's not usually, it's pretty straightforward to train this stuff. So usually, if I want to try performers, I would just turn on redrawing. If I use random features, then I would do 200, 300 random features, and that's it. But then I will probably try to turn off redrawing and see like whether that helps. Now, if you have deterministic performer, then of course, there is no question, right? Like you don't need to redraw at all. You don't need to use random features. So this kind of hyperparameters evaporate. So I would say, you can think about redraw as one yet like another kind of like hyperparameter. I would say like, there is a good default value, but definitely, I wouldn't say that no redrawing is necessarily a bad idea, because we have observed settings when it actually helped. So yeah, that's how it works. But yeah, this is a really good question. Like we did some like research on this, like redrawing, no redrawing on our own, because yeah, it's an interesting thing what's going on there. So yeah.
Great, thank you for the answer. Are there any other questions?
Yes, sure. First, thank you a lot for the great presentation and the great research, because
Thank you.
super interesting direction. It's to come back to the idea of applying performers to causal attention, so like in
Sure.
TV, that kind of stuff. Actually, we did quite a few experiments with performers, and we were quite impressed by the performance in general, by how much faster it is. But unfortunately, these kind of gains don't really translate in the causal attention. In the case of causal attention, mainly because the prefix sum isn't quite as optimized for, we have found. Is it something that you have any idea how to solve, or do you think it's a fundamental limitation of performers with causal attention?
Yeah, so this is a very good question, right? Like, so it's really about the causal variant. So yeah, so the bidirectional variant is beautiful, right? Like, because you don't need prefix sum, and that's good news. Now, the reason why the causal variant is tricky is that you need to incorporate that prefix sum operation. And you know, what is related to that is that, we observe that we need to write our own custom gradients for that block then, because if you use, let's say, like TensorFlow or JAX, and you ask JAX to do auto differentiation on the prefix sum, it's just not efficient at all, right? So that requires custom gradients. And that's what we did, right, for the causal variant. So with custom gradients, of course, you can make it, you know, at least like in principle, again, like efficient, right? Like, so space and time complexity is linear. And that's what we observe, like also like in practice when we run experiments. The point is though that, so as you said, right, like it's slower than the bidirectional version, right? Like, and it's slower, like exactly like for that reason, right? That you need like causal attention. That means really that you need custom gradients, and if you compute custom gradients, that really like you know, gives you like some. I mean, it implies like some extra time, and the mechanism is slower than the bidirectional version, like of the performers. So I would say that that is really, you know, the question. This is not like so much about the, you know, the algorithmic part of the performer, right? Like it's really about, you know, making sure that whether we use like TensorFlow, like or JAX, like or anything else, like you know, those the ways of I mean the support, right? Like for this custom gradients and stuff, like is really optimized like really well. So we, in terms of like what we are doing, right, like in order to, get like extra gains, right, like that's, I mean, the same gains that we have for bidirectional for the causal variant, we work with the JAX team. Actually, JAX was the first implementation of performance. So we work closely like with JAX team, like to improve like the prefix sum part, in particular, the custom gradient stuff, etc. So we do hope that you know, we will in a reasonable time frame be able to add like this, like improved like version like on open source. But this is really, you know, the question that I want to emphasize, right? This is like really more about the question about the infrastructure, because in principle this is still you know, everything is like linear here. You can do custom gradients like in the linear way. The point though is that you know, it's also like the question, like what is the range of like how long your sequences are, right? Like if you apply it like for the relatively short sequences where regular transformers are feasible, then, you know, of course, by adding this prefix sum operations, you are adding like extra terms that are negligible, right? Like for large L, but start to play important role where sentences are short, right? Like, so, I mean, simply because, well, standard attention is like very heavily optimized, right? Like it's just matrix multiplication and softmax. So so then, you know, adding this like extra terms, even if they are negligible, it is like you know, something that will play role if you have like very short sequences. Now, I would say that if you have a long sequence, then you know, there's not really any way to do it other than you know, with the prefix sum, like when you cannot really run like a feasible, I mean, unless like you want to add like some like structural priors, right, like regarding attention, like sparsity. What your setting was, right, like when you were applying the causal variant, like what range of L, right, like
Actually, it was a benchmark. So we looked at kind of all of the ranges we could, and we were looking for like the kind of breaking even point, you know, where like the performer became faster than the classic transformer. And I mean, this is totally what you said. I mean, we still, obviously, for very long sequences, the performer was the only way to go. So this is, I mean, this is completely true. And I mean, this is still a great great perks, I think of using the performer. It's just that the break-even point with kind of classic torch, and we did a few optimization, but probably not as deep as you did. It was not as the break-even point was not as early as for transformers, because for causal attention without the causality issue, but you can do just the matrix product and not the perfect sum. We found that the break-even point is super early actually, and even like for short sequences, what we consider short nowadays, is it's still well worth it to use a performer. So that's
right. Yeah. So I completely agree. I mean, causal attention is a little bit different beast, and a little bit more complicated one. Just because you add this mask, so you need the prefix sum. So in a nutshell, so we work right now on improving the infrastructure behind the causal variant, just to make sure that, I mean, as you said, right, if you have like very long sequences, really that's the way to go when transformer regular is infeasible. But to make sure that, you know, we can lower, right, like this kind of like further lower the lower bound on like kind of like when it makes sense to apply a causal performer, right? Like, so make sure that we can do it like even for shorter sequences. But that's really collaboration, like in particular with the JAX team, because that's exactly what we also like experience, is that you know, somehow when you I mean, the computing custom gradients, like even if you you know, everything is like linear, like in principle there is like some extra overhead, and you see it, right, like in experiments. I mean, the causal variant is slower than the bidirectional one. So it's a really good question, and you know, my short answer like would be, we are working on further like improving the causal one, so that it will be also very attractive also for much shorter sequences. But for like sequences like you know, 12K, right? Like for instance, the experiment like with ImageNet vision, like in general, I would say that, you know, that's the only way to go if you don't want to incorporate structural priors. Because of course, you know, you can try to sparsify, etc. That's a completely different story. So yeah, this is a really good question. Yeah.
Okay. Yeah. Thanks a lot. The answer was really nice. Thanks.
Thank you. Yeah.
Great. Other questions? Otherwise, I will ask mine. Okay. I will ask my questions then. Yeah, I have two of them actually. The first one is, there is, like, you put rightly a lot of emphasis on making this faster and everything, but also a common setting where transformers are used is like in distributed training. And are there any advantages in that setting in using performer over the traditional transformer? Sure. Or is it harder, easier, the same? I don't know.
Yeah, I think there are extra gains. You know, if you really look into that, the nice feature, right, is that you have the low rank decomposition. So if you think about this low rank decomposition, you can think about it like through the lens of Monte Carlo, right? If we talk about random features, or even deterministic features, right? I mean, let's focus on random features, like for kind of like for simplicity now. Then what we really do is we do Monte Carlo approximation. So you can actually use it for extra parallelization, right? Like what you can do is, if you need, let's say, lots of random features, I said that in practice 200, 300 is all that you need. But the point is that you can split these computations, like, I mean, computing like different random features by different machines. Or there are many ways of chunking, like the way how we kind of like distributing computations here, right? Like so one thing that you can do is you can do it along the random feature dimension. So you know, different workers can actually work in parallel on processing different chunks of random features. But there are like some other like interesting properties. Is that you can also well, the other dimension along which you can like split is the standard attention dimension. So let me get back. This actually, there's a good question whether we can use it somehow like in the distributed setting. But I want to mention it when we talk about like really how we can like improve further. So if we go like to the prefix sum mechanism, what you really see here, what's going on is, well, you just have like a prefix sum like operators in order to emulate the mask attention. And the point is that the really important object here is this outer product tensor. So we can think about this outer product tensor almost as a state of your current state. So when you take like a new token, then you transform the state by just like a matrix vector multiplication, and you continue. So the point is that you really just need to know this compact representation, the outer product representation, which is completely independent from the size of your from the length of your sequence. And that's actually an additional way of doing like partitioning like into chunks. So we actually have like follow-up like research where we work on that, and this immediately enables you to reduce memory footprint further. You can actually do this stuff even in the sublinear time. So the point is that you can leverage the prefix sum like operators to have a sublinear memory. That's what I meant. Sublinear memory computation of the attention block in the causal variant, and that might be also like interesting like from the point of view of I mean distributed computations, because what is very exciting is that you can, if you have lots of devices but with small with like limited memory constraints, you can still distribute your computations around like all these like devices. And use the observation that the outer product tensor doesn't really depend on the length of the input sequence. You can do this computation actually like in the sublinear time, even in the constant time. So we have like a follow-up paper actually on that, where we show that you can actually do it in principle like even in a constant time. Of course, the trade-off is time. But if you have lots of computational, I mean, lots of devices with small computational resources, you can, in principle at least, fully distribute it and pretty much do this chunking along the L axis in such a way that you will fit the memory on each device, and you will actually perfectly emulate causal attention. So that's like another like very nice feature of the entire mechanism. So I can actually even look like whether we have the paper. Yeah, so the paper is actually on arXiv, so I think I'm like kind of free to advertise it. It's called Sublinear Memory: How to Make Performers Slim. So by slim, really space complexity is sublinear, even constant. So this can be combined like with distribution, and so that's kind of like another like interesting angle. So all this stuff is the follow-up work that really comes like from this simple mechanism of disentangling, right? Like queries and keys, and having this low-rank representation.
Okay, that is super interesting. Thank you. I read the paper. Yeah, and then I have one last question. It's interesting that you showed like performer ReLU, and you talked about using different kernels, because I mean we use the softmax attention for some reason, mostly because in NLP we want something that's somehow unimodal, but like we are not forced to use that. And I was wondering if like you had experience in trying different kinds of kernels, and like maybe intuitions about where one of these makes more sense than other ones, these kind of things.
Yeah, so we have some research on that, and yeah, we don't have like clear conclusions. There are a couple of important observations that we made. Is that, well, first of all, not surprisingly, softmax kernel is really good, right? And it's really hard to beat it. Why that's the case, right? Well, because it's very picky, right? Like that's so you can really think about the attention mechanism almost like a dictionary. It's a mechanism for memorization where you kind of memorize a bunch of tokens, and then the new tokens comes and you associate it like with what you memorize. So it's really kind of like it's very combinatorial flavor, right? Like so softmax gives you this, right? Like it gives you this picky attention and almost like of the combinatorial flavor. So so what we observe is that well, in general, when we try these different kernels and different features, we want, well, I mean, first of all, you would like to have a kernel with positive values. That's kind of like obvious. I mean, you do this normalization, right? And you don't want like any negative values, but even more, when you try different kernel features, you would like to make sure that you have the mechanism that creates kernel features that are only positive. That was exactly the problem that we have like with regular approach to approximating softmax. If you use trigonometric features, the features are not necessarily positive. I mean, the dot product on expectation will be positive because it will give you the estimation of the Gaussian or the softmax kernel, but the features don't need to be positive. And that's the problem, because you have variance, and if you have very low values of your attention, then you can actually end up with the estimator that gives you negative values. So that's the problem. So what we observe is that you can try different kernels, but you want to make sure that the features that you create are always non-negative. So for instance, right, for favor plus, that's the case. And because it's an unbiased estimation of the softmax mechanism, you actually know that the variance will go to 0 as the entries go, the values of entries goes to 0, because simply there is no room. I mean, you cannot like have negative values. But of course, so my point is that, you know, when we talk about different kernels in the context of performers, what you really do is you construct different features, different kernel features, right? And so you come up with the new mechanism, right? Like it might be, you know, randomized mechanism can be deterministic. So you want to make sure that those features are non-negative. Also, you want to make sure that they are not bounded, right? Like because that's again like the problem, like with, you want to have like a picky attention, right? Like if you have like bounded features, you won't have like attention that like will be picky enough, and that hurts a lot accuracy. Now, of course, if you have unbounded features, that's another issue that you might run out into. And this issue is pretty much, well, some like numerical instabilities that potentially you might have. So it's kind of like, they are like, well, I mean, we incorporated a bunch of normalization methods like in the code. So you guys, practitioners, don't need to worry about really this stuff. And, you know, you just like use it. The stuff is going behind the scenes. But my point is that, you know, when the features are potentially very large, those dot products might be large, and you know, we kind of, because at the very end you are just doing normalization of the entire attention. Sometimes you don't necessarily need to explicitly compute these dot products and get like large values, but you can do some extra normalization. But anyway, these are like all technical details. The short answer would be, we tried different kernels. Softmax works really well. ReLU worked very well. The exponential kernel. So the exponential kernel, you just apply exponential mapping, and you have deterministic projections, even like canonical. So pretty much just even as simple as applying exponential mapping element-wise, and that actually also works like reasonably well. But you know, the other interesting question is hybrid setting, where you have different kernels using different heads. And that's an open question, right? So if you can like use like ReLU in that number of heads and softmax in the other, right? Is it like, does it give benefits, right? And there is no like clear answer to this right now, but that's something that, in my opinion, like is an exciting question. So I would say softmax is really good. You want something a la softmax, but what we still don't know, you know, like what are like the other variants. The performer ReLU works in practice really well in a bunch of applications, but there are settings where it's clearly a couple of % like behind, like in some like NLP like applications where you really want this approximate softmax favor plus. So this is like really, you know, complicated question, like what exactly, you know, which other kernels like would work well, but we have like some good understanding of what you need from this other kernel. So I would say like even from from the features of kernels that you are producing. Because the nice thing is that if you produce the randomized version, then you don't even need to know what is the explicit formula for the kernel. You just produce these features that are deterministic or randomized, and you just use them. So that's the nice thing. You can have like a very complicated formula for the exact formula for the kernel, but you don't even need to know it in order actually to apply this mechanism. So yeah, that's kind of like a couple of like you know, I mean, piece of information that we have like regarding how to choose these other kernels. But it's a very exciting area of research.
Great, thank you for the answer. It was very clear. I think time is up, so I will stop here, and I want to thank you again for your disponibility and everything, and the nice presentation. And yeah, I mean, have a good day. It's morning there, I guess.
Yeah, it's yeah, in New York. I would say in Jersey. I'm actually like in my home, like in New Jersey. Yeah, it's 11 a.m. So yeah, thank you so much for the invitation. It was a great pleasure to give the talk, and we are very excited like to see like that people actually use this mechanism. So there will be lots of new updates in the open source version, and just want to make sure that you guys can use it in your settings. I mean, the whole idea is to use computational, make sure that you know, with limited computational resources, you know, we can do what we do on the regular basis, like with large standard transformers architectures. Thank you once more.
Thank you again, and have a nice day. Bye bye.
Have a great day. Goodbye.